When I look out into the universe, I see many questions. But there is one question that space, at least for now, simply cannot answer for us. To get to that question, I need to walk you through what we think we know about dark matter, dark energy, gravity, space-time, the expansion of the universe, and its possible fate. Only then does the real gap in our understanding become clear. I want to start with something simple, the night sky. When you look up, you see stars. If you use a telescope, you see galaxies. For a long time, we thought that what we could see was more or less what existed. Then we started measuring how things move, and the motions did not match what we saw. In the early 20th century, astronomers began to notice something strange about galaxies. When we measure how fast stars orbit around the center of a galaxy, we can use gravity to predict the pattern. If most of the mass is in the bright central region, then stars closer to the center should move fast, and stars farther out should move more slowly, just like planets in our solar system. But when Vera Rubin and others measured rotation curves of galaxies, they found that the stars in the outer regions were moving too fast. The rotation curves were flat instead of falling off. According to normal gravity and the visible matter, those outer stars should have flown off into space. They did not. Something was holding them in. This was one of the key pieces of evidence for dark matter. The idea is simple in concept. There is matter that does not emit, absorb, or reflect light in any way we can easily see. It interacts with gravity, but not with light. We infer its presence because of its gravitational effects. Galaxies rotate too fast. Clusters of galaxies hold together more strongly than visible mass allows. Light from distant galaxies bends more than expected when it passes near massive structures. All of these point to extra mass that we cannot see directly. We have several independent lines of evidence. Galaxy rotation curves, gravitational lensing where light from a background galaxy is distorted by mass in the foreground, the motions of galaxies in clusters, the pattern of tiny temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, the large-scale distribution of galaxies across space. When we build models that include normal matter, radiation, and gravity as described by general relativity, they fail to match these observations unless we add a new component, dark matter. With dark matter included, the models match many different data sets at once. So we say about 85% of the matter in the universe is dark matter. Only about 15% is the normal matter that makes up stars, planets, gas, dust, and us. But what is dark matter actually made of? Here the universe becomes more quiet. It shows us the gravitational fingerprints of dark matter, but it does not yet reveal the identity of the culprit. We have some ideas. One class of candidates is weakly interacting massive particles, or WIMPs. These would be particles that have mass and feel gravity, and maybe the weak nuclear force, but do not interact with light. They would have been produced in the early universe, and then cooled down, moving slowly compared to the speed of light. That kind of cold, dark matter produces the right kind of structure. Small clumps form first, then merge into larger structures, building galaxies and clusters over billions of years. Another candidate is the axion, a very light particle originally proposed to solve a problem in the theory of the strong nuclear force. Axions could also act as dark matter if they exist in huge numbers. There are more exotic ideas as well, including sterile neutrinos and other particles beyond the standard model of particle physics. We have built detectors deep underground, inside mountains and mines, to shield them from cosmic rays and background radiation. These detectors wait for a rare collision between a dark matter particle and an atomic nucleus. So far, we have not seen a clear, repeatable signal. We have smashed particles together in accelerators like the Large Hadron Collider, hoping to produce dark matter in high-energy collisions. We have not yet seen convincing evidence there either. We have looked for indirect signals, like extra gamma rays or cosmic rays, from regions where dark matter might annihilate or decay. Again, no clear detection that everyone agrees on. So with dark matter, space tells us that something is there through gravity, but it does not yet tell us what it is made of. We know its gravitational behavior on large scales fairly well. We know how much of it there is, on average, from cosmological measurements. But we do not know its microphysics. We do not know its particle nature. That is one major unknown. Now I want to turn to something even stranger: dark energy. In the late 1990s, two teams of astronomers measured the distances and redshifts of distant Type Ia supernovae. These supernovae act as standardizable candles. Their peak brightness can be calibrated, so if you know how bright they truly are and how bright they appear, you can estimate their distance. Their light is also stretched or redshifted by the expansion of the universe. By combining distance and redshift, you can reconstruct how the expansion rate has changed over time. The expectation, based on gravity alone, was that the expansion of the universe should be slowing down. Matter attracts matter. Even if the universe started with an initial push, gravity should gradually decelerate the expansion. But the data showed the opposite. The expansion is speeding up. Distant supernovae were dimmer than they would be in a decelerating universe. That means they were farther away than expected. The conclusion: sometime in the last several billion years, the expansion of the universe began to accelerate. To explain this, we introduced dark energy. In our current best model, dark energy is a form of energy that is spread almost uniformly through space. It has a negative pressure. In general relativity, both energy density and pressure contribute to gravity. Positive pressure and positive energy density usually lead to attraction. But if the pressure is strongly negative, it can lead to a repulsive gravitational effect on large scales. That is what dark energy does in our equations. It drives accelerated expansion. The simplest version of dark energy is the cosmological constant, often denoted by the Greek letter lambda. It is a constant energy density of the vacuum itself. As space expands, the amount of vacuum increases, but the energy density stays the same. That means the total dark energy in the universe increases as the universe grows. In the equations of general relativity, a positive cosmological constant leads to accelerated expansion that eventually dominates over the gravitational pull of matter. We have several ways of measuring dark energy's effect. Supernova distances are one. The cosmic microwave background gives us a snapshot of the early universe, about 380,000 years after the Big Bang. The pattern of its temperature fluctuations depends on the geometry and contents of the universe. When we combine that with measurements of how galaxies are distributed today and how structures have grown over time, we find that about 70% of the total energy density of the universe is in this dark energy component. About 25% is dark matter. About 5% is normal matter. So most of the universe is something we do not fully understand. Dark matter and dark energy together dominate the cosmic energy budget. Yet we infer both of them indirectly through gravity and cosmic expansion, not through direct detection in the lab. With dark energy, the unknown is even deeper than with dark matter. For dark matter, we at least have plausible particle candidates. For dark energy, we do not even know if it is a true cosmological constant or something that changes over time. We can parameterize its behavior in terms of an equation of state parameter, usually called W. For a cosmological constant, W equals -1, exactly. That means the pressure is equal to minus the energy density. Observations so far are consistent with W equals -1 within the measurement errors, but they do not yet rule out small deviations. If W is slightly different from -1, or if it changes with time, then dark energy might be a dynamic field, sometimes called quintessence, instead of a constant vacuum energy. We also have a huge theoretical problem. If we try to calculate the vacuum energy using quantum field theory, We get a value that is many orders of magnitude larger than what cosmology measures. Depending on how you count, the mismatch is about 120 orders of magnitude. This is sometimes called the worst theoretical prediction in physics. So we have a quantity, the cosmological constant, that we can measure fairly well from the sky, but we cannot derive from fundamental theory in any satisfying way. The universe tells us the number. Our theories do not explain why that number is what it is. Now let me connect this to gravity and spacetime more directly. Our main theory of gravity is general relativity, proposed by Einstein in 1915. In general relativity, gravity is not a force in the usual sense. It is the curvature of spacetime caused by energy and momentum. Matter and energy tell spacetime how to curve. Curved spacetime tells matter how to move. This idea has passed many tests: the precession of Mercury's orbit, the bending of light by the sun, gravitational time dilation, the existence of black holes, gravitational waves detected by LIGO and Virgo from merging black holes and neutron stars. On many scales and in many conditions, general relativity works extremely well. We use general relativity to model the universe as a whole. We assume that on large scales, the universe is homogeneous and isotropic. That means it looks roughly the same in every direction and at every point, if you average over large enough distances. Under that assumption, the equations of general relativity lead to the Friedmann equations, which describe how the scale factor of the universe changes with time. The scale factor tells you how distances between galaxies change as the universe expands. The expansion rate, its deceleration or acceleration, all come from these equations, given the contents of the universe: matter, radiation, curvature, and dark energy. When we plug in the observed amounts of normal matter, dark matter, radiation, and a cosmological constant, the model fits a wide range of data. This model is called lambda CDM, lambda for the cosmological constant, CDM for cold dark matter. It is our standard cosmological model. It explains the cosmic microwave background, large-scale structure, galaxy clustering, gravitational lensing statistics, and the expansion history, all with a relatively small set of parameters. But there are tensions and open questions. For example, different methods of measuring the current expansion rate of the universe, the Hubble constant, give slightly different answers. Measurements based on the cosmic microwave background and early universe physics give one value. Measurements based on nearby supernovae and other distance indicators give a higher value. The difference is not huge, but it is larger than we would expect from random errors alone. This Hubble tension might be a sign of unknown systematics in the data, or it might be a hint that our model is incomplete, perhaps in the way we treat dark energy or the early universe. We also know that general relativity, as a classical theory, is incomplete at very high energies and small scales. It does not include quantum mechanics. We do not yet have a complete theory of quantum gravity. In regions of extremely strong curvature, like the centers of black holes or the very early universe near the Big Bang, our current equations likely break down. So our understanding of spacetime, while powerful, is not final. Now I want to connect all of this to the fate of the universe. The expansion history and the composition of the universe determine how it will evolve in the far future. In a universe dominated by matter and with no dark energy, gravity would slow the expansion. If the density were high enough, the expansion could eventually stop and reverse, leading to a big crunch. If the density were lower, the expansion would continue forever, but at a decelerating rate, approaching zero expansion in the infinite future. Dark energy changes this picture. If dark energy is a true cosmological constant with W equals -1, then the expansion will continue to accelerate forever. Galaxies that are not gravitationally bound to us will eventually recede faster than the speed of light relative to us, not because they are moving through space that fast, but because space between us and them is expanding. Their light will never reach us. Over time, our observable universe will contain fewer and fewer galaxies. Distant structures will fade beyond our cosmic horizon. On very long timescales, stars will burn out. New star formation will slow as gas is used up or locked into remnants. White dwarfs, neutron stars, and black holes will dominate. Black holes will slowly evaporate through Hawking radiation over enormous timescales, far beyond the current age of the universe. Eventually, in this scenario, the universe approaches a cold dilute state, sometimes called heat death. Matter and radiation are spread thinly. There is very little free energy to drive new structure or processes. The universe does not end in a dramatic event. It just becomes increasingly empty and quiet on large scales. If dark energy is not a constant, the story could be different. If W was slightly greater than -1 but still less than -1/3, the expansion still accelerates, but the detailed future changes. If W is less than -1, we enter the realm of phantom energy. In some models with phantom energy, the dark energy density increases with time instead of staying constant. The expansion accelerates so strongly that eventually it could tear apart bound structures. First galaxy clusters, then galaxies, then solar systems, then even atoms, in a hypothetical scenario called the Big Rip. Current data do not require this, and W equals -1 is still consistent with observations, but the possibility exists in principle if dark energy is more exotic. There are also models where dark energy decays or changes sign in the far future, possibly leading to a slowing of the expansion or even a future collapse. But these are speculative at this point. Observations today cannot tell us exactly how dark energy will behave over trillions or quadrillions of years. We only see a finite window in cosmic time. So we can outline several possible fates: eternal accelerated expansion with a cosmological constant, a big rip if dark energy becomes more dominant and more negative in its equation of state, a future change in dark energy leading to new dynamics, perhaps even a collapse, or something we have not yet imagined because our current theories are incomplete. Now I want to bring this back to the idea of the one question space cannot answer. When we study dark matter, dark energy, gravity, and cosmic expansion, we can ask many questions. What is the universe made of? How fast is it expanding? How did structures form? How will it evolve? For many of these, the universe gives us partial answers through observations. We build telescopes, detectors, and satellites. We measure light across the electromagnetic spectrum. We detect gravitational waves. We map the large-scale structure. Space, in that sense, is generous with data. But there is a particular kind of question where space becomes silent. It is the question of why these specific laws and values, and not others. Why this amount of dark energy, not 0, and not 1,000,000 times larger? Why this ratio of dark matter to normal matter? Why a universe where gravity is described so well by general relativity on large scales, but clearly needs quantum corrections at very small scales? Why a universe that allows galaxies, stars, and long-lived structures to form at all? From the point of view of observation, we can only measure what is. We can measure the value of the cosmological constant. We can measure the density of dark matter. We can measure the strengths of fundamental forces. We can test whether our models with these ingredients match the data. So far, lambda CDM with general relativity does remarkably well. But the deeper why these parameters question is not something the universe is obliged to answer through its large-scale behavior. We can search for clues. For example, if dark energy were slightly different in different regions of space, we might detect that as anisotropies or inhomogeneities in the expansion. So far, we do not see strong evidence for that. If dark matter had self-interactions, we might see differences in the shapes and density profiles of dark matter halos in galaxies and clusters. There are some hints and debates there, but nothing conclusive yet. If gravity deviated from general relativity on very large scales, we might see that in how structures grow over time. compared to how the universe expands. Surveys of galaxies and weak gravitational lensing are trying to measure this. So far, general relativity still works. In principle, a complete theory of fundamental physics might determine the values of these cosmic parameters from deeper principles. A theory of quantum gravity, or a unification of all forces, might have only a few truly free parameters, and everything else might follow. Or we might find that there is a landscape of possible universes with different values, and we happen to live in one that allows complex structure. But those are theoretical frameworks. The sky itself only shows us one realization, the universe we inhabit. This is the limit I want to highlight. Space lets us test how the universe behaves given the laws and parameters it has. It lets us constrain what dark matter does gravitationally. It lets us measure how dark energy affects expansion. It lets us probe gravity from the weak field regime of galaxies to the strong field regime of black holes and gravitational waves. But it does not by itself tell us why those laws and parameters are what they are. Even if we map every galaxy, measure every supernova, detect every gravitational wave, and characterize dark matter and dark energy perfectly in terms of their macroscopic behavior, we might still not know why the universe chose this particular combination. That why these laws and not others question might require a deeper theoretical framework, or it might simply not have an answer in the way we're used to in physics. Observations can rule out possibilities. They can favor some models over others, but they cannot tell us why the actual universe is not some alternative universe with slightly different constants. In practice, we do not stop there. We keep pushing. We build better surveys to test whether dark energy really behaves like a cosmological constant or not. We design more sensitive dark matter detectors and new experiments. We test general relativity on larger scales and with higher precision. We look for any cracks in the standard model of cosmology that might point to new physics. Each new observation is a chance that the universe will show us a deviation, a small inconsistency, that could guide us toward a deeper theory. For example, if we eventually detect a clear signal of dark matter particles in the lab, we will be able to measure their mass, their interactions, and their distribution in the early universe. That would connect cosmology to particle physics in a very direct way. If we find that dark energy's equation of state parameter W is not exactly Magnus 1 and perhaps evolves with time, that will tell us that dark energy is more than a simple cosmological constant. That would push us to consider new fields or modifications of gravity. If we find consistent, robust deviations from general relativity on cosmological scales, we might need to revise our understanding of spacetime itself. But even in the best-case scenario, where we solve the microphysics of dark matter, pin down the nature of dark energy, and unify gravity with quantum mechanics, there will likely remain a question that the universe cannot answer just by being observed. It is the question of why the fundamental structure of reality takes the form it does. We can hope that a deeper theory will reduce the number of arbitrary inputs, but we cannot guarantee that it will remove them entirely. So when I say the one question space cannot answer, I mean this. The universe can tell us how it behaves in extraordinary detail, but it may never tell us why its underlying rules and initial conditions are exactly what they are. We can measure the value of the cosmological constant. We can infer the properties of dark matter. We can chart the expansion history and predict the likely future. But why this amount of dark energy? Why this balance between attraction and repulsion? Why these ingredients that allow a universe with long-lived structure instead of a brief, chaotic flash? Those are questions that might lie beyond what observation alone can resolve. Right now, one of the sharpest open scientific questions that sits at this boundary is very concrete. Is dark energy truly a cosmological constant, with W equals -1 fixed in time and space? Or is it something dynamic that changes over cosmic history? Our telescopes and surveys are trying to measure that number and its possible evolution with ever greater precision. The answer will tell us not only about the fate of the universe, but also about how far our current theories can go in explaining the deep structure of spacetime itself.